All right, is everyone all settled down? All right, great, let's get started. Hi everyone, this is Reflecting on Hat, a Project Babylon case study. I'm Ruby, and just as a show of hands, how many of us went to Paul's JavaOne AI presentation just now? Okay, that's a decent amount. So that's really great because this presentation will build upon some parts of Paul's presentation, specifically for Project Babylon and code reflection in Hat. And this will involve some technical discussion of its projects and how the API is used. But if you didn't go to his presentation, that's also okay because we'll have a brief overview of everything that's related to this talk. All right, let's get started. I think we can all agree that Java is quite a powerful language. It has extensive APIs, libraries, and frameworks that allow users to do everything from creating machine learning models in Java to consuming large amounts of data through parallel streams. However, there's still a lot that Java can't do. For example, in the case of executing parallel tasks on many threads, we are limited by our CPU's thread count. If we can use something like a GPU instead with its many threads and specialized architecture, it would greatly enhance our data processing capabilities and reduce overhead. But we don't have a good way to connect Java to the GPU. The GPU simply just doesn't understand Java. We could try writing device-specific code, such as writing CUDA code, then using JNI to compile and execute that code. But this requires Java developers to know CUDA, and this isn't platform independent. So how exactly can we extend Java's reach to these foreign programming models while still maintaining Java language constructs? We'll try to answer this question today through exploring code reflection and its application in Hat. So here's a small agenda for today. We'll be going over code reflection and then Hat, just some basics. And then we'll be looking at two sort of case studies within Hat of how we transform and analyze code models in order to enhance the Java-ness of its API and also to increase performance. Next, we'll have a brief demo, and then finally we'll be going over future plans for these two projects. All right, let's talk about code reflection. Code reflection has been introduced by Project Babylon as an extension of Java reflection. We have a JET proposal going, and we're currently preparing for incubation. Code reflection enables access to what's called a code model of Java methods and lambdas. A code model is a symbolic representation of Java code, which takes the form of an immutable tree structure. And these models are in static single assignment form, or SSA for short. This design is inspired by MLAI and also LLVM-based compilers. And these code models are created for methods and lambdas that are annotated with @reflect. We can also traverse, build, and transform these code models, which we'll be going into in a bit. But first, let's take a look at how code models are generated. As mentioned earlier, a method or lambda needs to be annotated with @reflect for a code model to be generated. So here's a simple method, and let's walk through how it's normally compiled. So when a Java program is compiled, the source code gets transformed into an abstract syntax tree, or AST for short. An AST retains a lot of syntactic details from Java source, but those details get transformed away when ASTs are further broken down into Java bytecode. This looks more similar to machine instructions than an AST does, and a lot of details get abstracted away. For example, characters and shorts become integers, and for and while loops turn into goto branches. Well, where does the code model sit in this? Well, code models are generated using the AST. It sits between the AST and bytecode in terms of complexity, and we can also generate bytecode from the code model. Now let's break down what a code model consists of. For a simple method, the code model will generate a tree of code elements, like so. Each code element can be represented as a node inside of the code model's tree. For ease of use, we can also print out a textual representation of the code model, like so. In general, this is going to be how we represent code models from here on out inside of this presentation because it's simply easier to read. And every element in the code model can be broken down into three categories: bodies, blocks, or operations, which we may call ops for short. First, let's talk about operations. The root of every code model is an operation. In this case, it is a func-op or function operation. Subsequent operations model variable declarations, arithmetic operations, method calls, and more code structures that are present inside of the original source. Every operation can have any number of bodies, and this func-op contains one single body. A body can contain one or more blocks, and in this representation, we see that there is only one block inside of this body, and because we printed out the textual representation, the body and the block are fused together for increased readability. If we look at the tree representation of this code model, it's easier to see the difference between the body and block. This is a different code model where you can see a clearer difference between bodies and blocks. This is representing an if operation, or if-op for short, and each block inside of the if-op's body represents either a branch that the if-op may take, or a block that contains the conditional that is evaluated inside of this if-op. Every block will end in a specific type of operation, which is called a terminating operation. Now, this includes returns, gotos, or anything else that would break control flow. For those familiar with SSA, a code model block is pretty similar to a basic block. And finally, every block also has its own set of parameters. Moving on to results, every operation inside of the code model has a result that's stored. And it is denoted by a specific type, such as integer or double, and is referenced by, if you see the percent symbols, those are basically how we refer to those results in future or subsequent operations. Before we can do anything like traversing or transforming these code models, we of course need to access them first. To access a code model for a method or lambda, we first retrieve the corresponding core reflection representation. For example, for a method, we retrieve a method instance. We then pass the method instance into code reflection, which will retrieve the corresponding func-op, like below. Finally, we can start traversing through these code models. Now, in order to do so, we can walk over a stream of these code elements in the code model. We can do this by calling the elements method, and we can iterate over each individual block, body, and operation. And this is roughly how we end up printing out the textual representation of these code models as well. We can also filter for specific elements inside of the code model as we traverse, such as certain operation types that we want to analyze in more depth, like this variable operation. We can also construct code models through the use of builders. If we want to create a new function operation, for example, we need to build its name, parameters, and the code elements inside. We first create a body for the func-op and then append operations to what is called a block builder that constructs the new code model's elements. We can also add elements to the block builder by passing them to the op method, which will return a result. And this result can also be used in subsequent operations as operands. Models will be checked to ensure that they are structurally sound, so we need to make sure that every block ends in a terminating operation, such as the return operation in this example. One of the key features of code reflection is transforming these code models, which is a combination of traversing and building code models. To do this, we first pass in an existing code model as an input. We traverse the inputted model, building a new code model based off the input and any new rules specified by the user. Finally, we output this new code model as a transformed model. Although these code models are immutable, transforming it makes it possible to modify the semantic meaning of code models and therefore Java programs. Well, if our goal is to traverse and analyze Java code, why do we need code models? Well, in the first place, ASTs are too high level. They aren't easy to manipulate, and there's a lot of syntactic noise inside of the tree. Furthermore, bytecode is a little too low level. It's optimized for the JVM, and it also translates away a lot of source code information. Code models are a sort of Goldilocks spot between the AST and the bytecode. It retains the structure of the AST while also lowering the code as much as we can to bytecode. And using these transformations, we can take the code model of Java source, transform the model, and execute bytecode generated from the transformed model. This way, we can create new semantic meaning inside of this Java code. For example, if we want to add logging statements inside of an existing program, we can do that. Or we can translate Java to foreign programming models by passing the code model to libraries for translation. These code models retain just enough semantic information to make this transformation much easier. And this enables various capabilities for Java programs, including differentiable programming, link-style queries, machine learning modeling, such as Onyx, and GPU programming. So let's dive into how we can enable GPU programming using code reflection through the usage of HAT, or Heterogeneous Accelerator Toolkit. If we break down the name of HAT, we can elucidate its purpose. Heterogeneous stands for a variety of devices and their corresponding languages. Accelerator stands for hardware accelerators, such as GPUs, CPUs, and FPGAs. And Toolkit is just a set of libraries. So, Heterogeneous Accelerator Toolkit, or HAT for short, is a set of libraries that allow parallel algorithms to be written in Java and executed on various devices. HAT has been empowered by new projects such as Project Panama and Project Babylon, which enable its access to foreign programming models. In particular, HAT uses code reflection to model GPU constructs such as vector arrays, and HAT converts Java code into CUDA, OpenCL, or other device languages before executing on these devices. In fact, much of HAT operates on the code models that are generated by code reflection. And one of the goals of HAT is to demonstrate that Java can be competitive in the field of AI and GPU compute. So this is a diagram of how HAT interacts with Java source and the general compilation stages for HAT code. So on the top level, we have Java code. So this is a mix of just regular Java and HAT-specific code. Underneath, we have the HAT API, Panama FFM, and code reflection, which helps with communicating with accelerators, such as GPUs. Next, the Java application is executed on the JVM, and the accelerated parts of HAT are dispatched through the HAT runtime. We aim to maintain a pluggable backend, which is one of HAT's strengths, where we allow us to dispatch to various vendors, such as CUDA and OpenCL runtimes, and users can also develop their own backends to support other languages. We've previously had support for things like PTX, SPIR-V, HIP, and anything else that you can think of. HAT also enables dispatching kernels through Java, which is very useful for debugging these kernels. Finally, the JVM sits atop the CPU, while offloaded HAT code sits on top of accelerators, including GPUs. To understand how exactly HAT works, let's take a simple example and try to parallelize it. This is a simple loop for squaring every element inside of an array. And if you note, every operation that occurs on the array is independent of the other elements and can be parallelized. We can extract the exact squaring of the elements into a separate method, like so. This method will become our kernel method, the method that is run on every single thread, and each thread will be passed an array and an index to take the square of. We need a method to call or dispatch the kernel method, and we also need to compute what indices to square over inside of the array. Here, this computing method calls our kernel method for every element inside of the array. Finally, we have our main Java code that may call the computing method and use the results in some specific way. And from these three components, we can derive the HAT programming model as such: a kernel layer, compute layer, and regular Java code. This is a slightly simplified version of HAT, but the core concepts are still here. First, we have our kernel method. This holds accelerator code that runs on every single thread. And although the code looks kind of different from the code that we had initially, the semantics are virtually the same. If you notice here, arrays are modeled using classes, Here we have an S32 array that is simply an integer array, and we'll get into why exactly we need these classes to model these arrays. Each kernel also has a kernel context that's passed into the kernel that may be used for calculations. And the kernel is also converted to the device language through code reflection, hence the need to annotate the kernel with @reflect. The compute method is a little more different from the starting code because although it's semantically the same, we have our own API for dispatching the kernel over a given ND range, n-dimensional range, or our workspace. That is the size of our array. We also pass the kernel context to the kernel method so it can access the thread's ID and other information that may be used for calculations. And finally, we reflect across the compute method to expose points of optimization, especially across these kernels. Finally, the compute method is called from just regular Java code. And here we also initialize any global arrays that are used inside of the kernel and then pass to the compute layer. This also creates an accelerator to model what backend we're going to be using and what to dispatch to. And if you notice, there's no need to annotate this code with @reflect, since none of this code really needs to be translated into device code. So we mentioned earlier that code reflection is used throughout HAT, but where does it come in? We use it for retrieving the kernels and compute methods for transformation and analysis. These next two sections will be deep dives into two examples of how HAT uses code models to enhance the Java-ness of its API or to optimize its execution. First, let's talk about array views, which is one way that HAT uses the code model transformations to strengthen its ease of use for Java developers. So as you might have noticed earlier, instead of our typical array accesses, which are referred to as buffers in HAT, we access these buffers through methods. Why? In the first place, we need to use off-heap memory when modeling these buffers. This gives the device the opportunity to allocate memory in its own optimal space. And since Java doesn't own this off-heap memory, this avoids garbage collection. To model off-heap memory, we store data inside of memory segments, which are bound to memory layouts. These are features introduced by the Panama API and are constructs that are passed by HAT to the device layer. Interfaces expose methods that operate on these memory segments, and buffers are tied to such interfaces. We could have exposed memory segments to the user, but I think that operating on these interfaces is much easier. And on the bottom, we have a small diagram comparing how you would normally code something in just regular Java versus using HAT arrays. It's not too different, but there may be issues with how HAT represents its buffers. The code can get really verbose with complicated pointer arithmetic. This is harder to write and even harder to debug. If we could write this like we would normally write code in Java, using your typical array accesses, it would be much simpler to write this code and maintain it. Like this. Ideally, this is how we would write our code inside of HAT. This is easier to read, but we still need to maintain the use of these interfaces and memory segments in the backend. This isn't really negotiable. Ultimately, we want to mimic how arrays are used in Java while still maintaining the same backend. And this can be accomplished with code reflection. On the left is how we would like to access our buffers in HAT, and this would be found inside of our kernel method. On the right is the code model that is generated from that line of code, and we use this code model in the backend of HAT to generate the device code. And the thing is that this isn't the code model that HAT can consume. This is. Over here, we use interfaces to modify these memory segments. And if we can transform the generated code model into the code model that the backend understands, then we can support the array view that the programmer sees. So this is where we tell a little white lie to the user. It looks like buffers can be accessed as if they're typical arrays through the array view. But in the backend, we convert the array operations into method calls. We can possibly cast the index type to match the type of method call, and we can turn arrays, loads, and stores into getters and setters. On the left is an example of how you might transform a code model. So for array views specifically, we want to be extra sure that we maintain the semantic meaning of the code model despite changing these operations. Let's walk through how we might use transformations to support array views. So let's start with transforming the example that we saw earlier for accessing an array at a certain index. As we begin the transformation steps, we first encounter a variable load operation. This matches one of our conditions inside of our switch statements for something that we may transform. This is because some buffer loads need to be replaced or removed if they involve array views. However, we can tell that this operation is not loading a buffer. It's loading a kernel context, which is not a buffer. So this will fall through the default code, and it'll be copied into our outputted model. The next operation that we see is a field load. So this also isn't handled by our transformer because fields are separate from buffer accesses. So this too will fall through the default code and get copied over into our outputted model. Finally, we encounter the array load. Now, this does need to be transformed into an invoke operation. So whenever we prepare to add the invoke operation, we need to first check to see if the parameters passed into the invoke are of the correct type. If not, we need to add a casting operation. So here we have a conversion operation to cast the integer index into a long. And next, we can create our invoke operation to replace the array load. Specifically, we need to use core reflection to determine which getter and setter we need to use inside of our invoke operation. Finally, we map the result of the array access to our new invoke operation. This means that if the input code model uses the result of the array load in future operations, the block builder will know to substitute that value with the result of the invoke operation. And that completes the substitution of the array load inside of the code model. With these transformations, we can achieve this conversion between the two code models. But how does this look for more complicated models? If we were to access a 2D array, for example, the code model will generate several lines of pointer arithmetic to calculate the correct index. The code model actually, from a 2D array, retrieves a 1D array row from the 2D array, and then it extracts the actual value that we want from the 1D array. Following the same transformation logic as earlier, the hat model becomes similarly as large. And honestly, this feels a little unnecessary, and it makes the code model really hard to read. All that hat really requires from this model is what array is accessed, at which indices, and whether this is a load or store. Is there a way that we can condense this code model if we can store the relevant information for the array accesses into just one operation? Yeah. We have a thing called custom operations inside of code reflection, and by extending the op class inside of code reflection, we can create custom operations to model new and foreign structures. In this case, we create a pointer operation to hold the information extracted from array views. Hat also supports other custom operations like vector ops, which provide users with access to accelerator and GPU-specific data structures. A collection of these custom operations inside of a library can form a code model dialect, such as the hat dialect. Hat currently supports its dialect through a series of transformation phases. Currently, we have different phases to support different parts of the dialect, such as a phase to handle array views, and the backend then consumes this custom code model and then generates the device code. With custom ops, we can convert the array-related operations into one pointer operation, and the transformation stage is therefore simplified significantly. If we were to try transforming this 2D array code into just one pointer operation, we need to examine the code model for the root of this array load. This is the operation that contains all of the access information that we need. Not all of it is directly stored within that array loads operands. A lot is stored in previous operations that can be accessed through these operands. And in order to do that, we have to traverse backwards through this graph, through the array loads. And we can encounter first one of the array indices that are used to access it. And then traversing further backwards will reveal the other indices that we need. And finally, we can create a pointer operation that contains all the essential information for the buffer access. And this pointer operation will be further broken down by the hat backend. Ultimately, despite using array views and pointer operations, we can create the same device code as if we never used array views to begin with. And as we can see through the usage of array views, transforming these code models are key to supporting dialects and maintaining Java constructs while accessing foreign programming models. These transformations on the code models strengthen the Java frontend of HAT, but they also support foreign dialects through the usage of custom operations. Now let's take a look at how HAT uses code reflection to analyze code and perform optimizations through the usage of buffer tagging. Normally, when we perform computations on the accelerator, we need to transfer data between the accelerator and our local device. However, every data transfer is extremely time costly. We can introduce a performance enhancement when we minimize these buffer transfers, and therefore reducing the number of times we copy data to and from the accelerator. Usually, these buffers are tagged as read-only, read-write, or write-only, and the number of minimum transfers that we can do depends on the access type. For example, if the accelerator is only reading a buffer, we transfer once to the accelerator. Read-write has to be in both directions because we need to read and write, and write-only means that we only transfer from the accelerator. However, determining what buffer is read-only, read-write, write-only is pretty difficult. It gets hard to trace these buffer accesses, especially in more complex kernels. Initially, we manually tagged these buffers in HAT, but this can introduce opportunities for human error and therefore incorrect buffer transfers. Ideally, we would automate this process. One particular challenge about automating this process is if the kernel method calls other methods. HAT kernels may pass buffers to other methods that will help with computation. And when we track these buffers, we need to follow them across method calls. But mapping buffers to parameters may become cumbersome with many possibly nested calls. There's a cleaner way to approach this issue. We can insert the contents of the invoked methods inside of the kernel method. In essence, we're inlining the method calls into the kernel method. This allows us to analyze the kernel and invoked methods in a single pass, removing the need to map buffers to parameters across calls. Let's take a closer look at what inlining would entail. Inlining a method, which we'll call the callee, into the kernel, which we'll refer to as the caller, is simple when we only have one return point inside of the callee. We can simply insert this callee's code into the caller without changing or adding any control flow. In this example, we can tell immediately what value will be stored inside of this array. However, when we have multiple return points inside of the callee, it becomes less obvious how to inline this into the caller. This is a simple example, but inlining larger methods will become more difficult and just generally harder to merge the control flow. We can't simply insert the callee's code into the caller. We could potentially replace the return statements inside of the callee with the caller's array accesses, but we want to avoid modifying the caller. All we want to do is insert the callee's code. Well, code reflection makes this much easier. These are the corresponding code models from the methods that we saw earlier. And visualizing these methods as code models actually helps us figure out how to combine these two. The key point is that we have two different return points inside of the callee's code model, but we need one entry point and one exit point in order to inline this into the caller. we can't exactly merge it as it is right now. First, we need to unify the control flow within the callee by creating a single return point where the previous return operations become branch operations to our new return point. And this way we can merge the callee's control flow and make it possible to merge the two code models like so. On the right is our inline code model. And here is generally how that would look inside of Java. You might notice that this is a little different from our code models from earlier. This is because Java source can't directly model all of the different types of branches present inside of our code models. But for our purposes, we're staying within the code model realm to analyze this Java code and create optimizations. So as you can see, by unifying these return operations, we can successfully inline this callee. And when applied to these kernel methods, this lets us trace buffer uses in a single pass. After merging the code model through inlining, we analyzed the code model in order to automate this buffer tagging process. We can walk through the inline code model, tagging any buffer accesses with read-only, write-only, or read-write. And this is the inliner code that achieves the inlining that we walked through earlier. This will iterate over a method and append each operation to an existing code model. And the highlighted portion is the code that actually handles the return operations, as mentioned earlier. So if we need to merge control flow into one return point, we create a new return block to hold the new point here. We also need to iterate over these method calls inside of the kernel method, inlining as we go. So this is the inliner loop for that. And now we can iterate through the code model that is now inlined and tag these buffer accesses. Our primary focus is on these invoke operations, which is how these buffers are accessed. We store these tagged results, which can be used to minimize buffer copies to and from the device. And hat actually has a minimize copies option, which will pass the tagging results to the backend. When we tag these buffers, we walked through the kernel and look for buffer accesses denoted as invokes. So in this example, we need to first identify the invoke operation we come across. So this is an array load because it returns a result as an integer. And to determine which array this corresponds to, we need to use the operands to walk back inside of the code model. And we see that this array load corresponds to the array that is symbolized by 4. So we store this as a read-only for now inside of our buffer map. Next, we see an array store because this invoke operation doesn't have a return value. So as we walk backwards through the operands, we see that this is a store on the same buffer that we accessed earlier. So this is a write on a buffer that we read earlier. We'll update this buffer's tag as read-write instead of write-only because we both read and wrote to it. Finally, we have one last invoke operation, which is also an array load, but walking backwards through the model, we see that this is on a different buffer. This is on buffer 5. So we add this into the map and we can designate this as write-only. Buffer tagging reveals that we can derive value from code models even without translating them to foreign programming models. Code models can also be analyzed to reveal these optimizations within the code. All right, so now we have our demo of what is called Game of Life. It's one of the examples within the hat repository. So let me just pull this up. This is a clock, I believe. Oh, it's on my screen. This is a clock made by Conway's Game of Life. So if I start that, this is run using the Java sequential backend. So there's no parallelization going on right now, so it's quite slow. You can see like every single iteration going on. So if we want to accelerate this, make this faster, we can use the hat backend over here. Let's try running this using OpenCL. And I'll pull that over. So that is our OpenCL backend for the game of life example, and it's significantly faster than before. You can see just the performance increase in the example. But this still has a lot of extraneous buffer transfers. So if we enable our buffer tagging, you can kind of see the clock coming in. Let me exit this. So this is enabling our minimize copies option within our kernel using the OpenCL backend still. And if I pull this over here we have basically twice the performance. So, and this is without a lot of optimizations that we could be doing on the kernel. We could be doing perhaps like optimizations across kernels, further additions to HAT. But even with just a basic minimizing the buffer transfers, we achieve basically twice the performance as earlier. So if I keep this running, the clock will change. Right now, it's still stuck at 12 o'clock. So switching to the actual code of HAT, this is the example, and you can see that's some CUDA code. So this is the kernel that is used to create this clock. And you can see we access everything through these buffers over here. And it's basically just Java code thanks to code reflection. If I were to use array views instead of these buffer accesses, like so. The mouse is so slow. Okay, and so instead of using all of these extra methods to modify our buffers and do this pointer arithmetic, we can simply use them as if they're just regular 2D arrays. Let me stop that. And then let's recompile. So currently we're recompiling everything inside of the HAT backend, and then after it's done, we can see that the example will be essentially the same as before, despite using a completely different way of programming these kernels. So over here, we start it, and basically it works as if you didn't even use these array views. So going back to the presentation, what's next for code reflection in HAT? Well, code reflection is a powerful tool that allows us to transform Java code. We can translate to foreign programming models or execute this code as bytecode. And we can analyze models to reveal and create code optimizations. HAT demonstrates the power of code reflection in extending the reach of Java to foreign programming models. Parallel programs can be executed efficiently through Java or on accelerators, and in particular, debugging and testing through Java provides a huge advantage for HAT compared to similar implementations. Code reflection also supports the use of Java constructs and syntax within HAT. In terms of moving forward, code reflection is moving towards incubation and eventual public release. We have new features that we're looking at, such as pattern matching, code model querying, and more. And in general, we're just looking towards additional tooling for analysis, transformation, and visualization. And we're actually open for public contributions. So if any of this interests you, if you want to play with the APIs, feel free. And we are also, in regards to the reflect annotation, we're aiming to become a language construct, or language feature, so hopefully this goes away in the future. In terms of HAT, we're exploring its potential in terms of creating powerful, efficient, parallelized programs with its robust dialect. So we're exploring local and shared memory and their applications within HAT. We're expanding our own tooling for code methods, and we're generally adding more support for device types through dialects and code reflection. So this may involve various vector types, tensors, even tiles, etc. So if any of this is interesting to you, We have more presentations about Babylon, Hat, code reflection coming up. But that's everything. Thank you for coming to my presentation. All right. If there's any questions, feel free to ask. Yes? That's a good point. I think we have considered that. And for our purposes, these code models may be modified or transformed by other parts of the backend. So it's really easy for these code models to become out of date. So if we have an existing mapping of a code model, that may end up becoming obsolete. So we try to essentially reference something that doesn't exist later on, for example. So by inlining these code models, we essentially avoid that issue in the future.
Thank you.
Mm-hmm. Yes? Yeah, I think in terms of custom operations, it's essentially making it easier for people to code for specialized backends. So with Hat, it allows us to use these accelerator-specific or GPU-specific constructs from Java so that we don't need to add any additional hoops for these programmers. They can simply just code regular Java and that'll be converted over. So it's really good for creating these dialects. So in terms of Hat or Onyx or other backends that you want to translate Java to, it's, I think, fairly useful in those applications. Yes.
I noticed there was a gets and sets.
I don't believe we have support for that right now,
Okay.
but it is definitely something to consider. Yes.
So how would you control launching kernels? Typically in CUDA, you decide how many blocks and how many threads you're going to launch. How do you do that with Babylon? You have a kernel, but you have to specify dimensions, how it's going to be executed, not on a one-dimensional array, but you have three-dimensional arrays or something like that.
Yeah, so in terms of specifying the workspace, I can probably pull that slide up, but you are able to determine what kind of workspace you want to use for these Hat kernels. If you want to learn even more about it, I believe Juan's presentation should go pretty in depth about it. So I highly recommend that. But yeah, the Hat backend will generally handle this, the dispatching the kernel, determining the workspace, and everything else related to the devices.
Just a comment, the performance, that may significantly improve the performance. Mm-hmm. Because how it is going to map to the actual hardware, it's the trick of CUDA programming.
Exactly. Right. All right, thank you guys.